Okay, moving on. Friends, if you have been working on some countermeasures or offensive research when it comes to hardware security, our CFP is open for the Netherlands edition, which is going to be physical in October. So please do send in your submissions to us. We would love to read your research as well. The next talk for the day is by Eric Evenchick. He's a director at Linklayer Labs and also a trainer at hardwear.io. The training that he delivers is reverse engineering using Ghidra. Eric will introduce a new tool today with us that's used for the automotive industry for reverse engineering, which operates by dissecting the CAN protocol, injecting malicious code, thus surrendering controls over the automotive systems to a hacker. The talk title is Building CANtact Pro. So Eric, over to you now.
Hello, thanks for the introduction, and thanks everyone who's sticking on here with I think this is the last talk of the day. So thanks for sticking around. Let's fire up some slides there. So yeah, name's Eric Evenchick. I have a company here, Linklayer Labs, that does embedded security consulting, training, and some tools, including some open source stuff, including the CANtact products, which are open source CANBus tools. So just going to take you sort of through the journey of building the newest version of that product, and just some interesting things that came up along the way, and why we built it, and what we ended up with. So just very quickly. This always depends on the audience. I think there's probably some folks on the call here that have played around with CAN before, and probably some that have never seen it. But CAN, or controller area network, it's a somewhat common networking topology used mostly in things like cars. Also pretty popular in SCADA and industrial control systems. You'll find it also in the aviation world, though sometimes under different names, for things like avionics. Motor controllers use this a lot in industrial settings. So there's a lot of different applications where you'll see this used. And in practice, it's kind of similar to, oh, sorry, I got the presenter view covering that. There we go. In practice, it is similar to other networking you'll see between embedded controllers. So for example, SPI or I2C or something like that. The big difference with CAN is it's most commonly used for connections between different controllers, so off the board. And also it's a multi-master bus. This makes it quite a bit different than a lot of those types of systems, just because there is no single master controller that you need to rely on. You can have a bunch of different controllers, and all of them are able to talk, even if one of them drops off the network. And this is actually pretty important for things like real-time systems or high safety critical systems, because if your say engine controller fails, you don't want your brake controller to suddenly also fail. So having the ability to lose a single node is actually a pretty good feature. There's also some other real-time relevant features like message priorities. So between the message priority and arbitration scheme in CAN, it's actually pretty simple. The lowest. So what you'll see is that with CAN frame that gets sent out, whoever has the lowest ID during the arbitration phase will win, and that allows you to do some prioritizations despite having multiple masters. And every frame gets a hardware level CRC, so you get some level of integrity checking, though not against an attacker. And this often brings us to the problem with a lot of CANBus systems from a security standpoint, which is that the networks tend to be trusted in the sense that when you send a CAN frame, everyone on the bus is going to believe that it's real, and they're going to process that data as it's received. And this has led to a bunch of different good demos and attacks, but the way that I honestly look at this now is if an attacker has the ability to send arbitrary frames on a CANBus, it's kind of like having a root or ring zero access in a sense. It's that very high level privileged access, so it's compromised. That being said, there are some mitigations that are in the works for those types of things. Now, CAN itself is a very low-level protocol. It lets us send 8 bytes of data at a time, but there's some interesting higher-level protocols that come into play. So there's this thing called CANTP or ISOTP, depending on what name you want to use. This is used to string CAN frames together to make longer payloads of data. So again, 8 bytes per frame is sort of a limiting when you want to do something like a firmware update. So this protocol allows you to chain together up to 4,095 bytes of data into sort of one message by sending multiple frames. And that's still very limiting in terms of doing a firmware update, but by chaining those together, you can end up actually fully updating controllers. On top of that CANTP and ISOTP, we'll see things like Unified Diagnostic Services, which is the ISO 14229 standard. This is the protocol that whenever you bring your car into a dealership and they plug in, there's a very limited subset of what are called the OBD functionality, onboard diagnostics. This is a standardized format that you can buy those off-the-shelf tools for. The version of OBD2 that's out there right now, you'll find in every car made after about 1996. So that's a very basic interaction. It'll get you some fault codes out of the device or out of the engine controller. You can clear fault codes and read some data. Unified Diagnostic Services is a whole bunch of extensions to that. They are proprietary. They're specific to whatever manufacturer you're looking at. And they'll let you do all sorts of stuff. Every diagnostic feature that your dealership can do is done over this. So everything from reflashing controllers to calibrating sensors. You can do things like dump the airbag recorded data using this protocol on some vehicles. You can even deploy the airbags using this protocol on some vehicles. So yeah, there's a lot of functionality that's baked into there. CANopen is another protocol that you'll see mostly in motor control. It's just sort of a add some addressing and stuff on top of CAN to make it a little bit more practical for a well-defined network where you want to have these off-the-shelf controllers that can talk to each other. Not so much in cars, but SCADA and ICS that will come up. And then CCP and XCP, the CAN calibration protocol, and the X meaning anything calibration protocol. These are used during development of ECUs in some cases, so they'll provide development access over CAN or other interfaces. Occasionally you'll see them left enabled. This has mostly been fixed from what I've seen, but for a number of years you would see this left enabled in production vehicles, and it would let you do things like read and write arbitrary memory addresses, which obviously creates a whole host of vulnerabilities that you can exploit. So basically, CAN is this somewhat obscure but very interesting network that you find in some pretty high criticality systems. So back in, I think it was 2014, I launched this little open source hardware thing called the CANtact version 1. And it was a CAN to USB device. It was a super cheap to build and everything, CAN to USB device based on the STM32 F0 microcontroller. And honestly, the reason I chose this microcontroller and the reason that this design came to be was that ST came out with it. It was sort of the first low-cost microcontroller that could be both a USB master as well as or USB device, sorry, as well as a CANBus device. There were not too many microcontrollers out there that would do that. Most of them were very high-end sort of applications processor. So this allowed me to build something really cheap that would do this. And at the time, especially, there were not many options out there in terms of open source or even low-cost hardware for CAN. Some of the cheaper options would be things like the Intrepid Control Systems devices, which were in a couple hundreds of dollars and didn't really have much software support until you were paying sort of in the thousands of dollars. And then the most commonly used devices would be in the thousands of dollars by the time you bought the software and everything easily. So this device came out with the main purpose or main support being SocketCan on Linux. And because this microcontroller was cheap and had all the hardware, a few interesting things happened. So someone wrote a much improved firmware called Candlelight that talked to a driver that was built into the Linux kernel, and still is, meaning that out of the box, you can plug this in and you actually get a network device on Linux. And so that's, quite useful in terms of being able to very, quickly get up and running. There's no drivers to install in Linux. However, it had no isolation, so there's an electrical connection from the CAN side to your computer. It's a single channel, so there's just one CAN channel there. But hey, it was cheap and it got forked by a number of people. Ethan Zonka made the Candlelight device by Hubert there, who did the firmware, and Vulkan and so on and so forth. And many of these were actually really interesting improvements or targeted a niche. So for example, Ethan's Cannibal, he was doing a hydroponics installation, I believe it was, and he wanted a device that had just screw terminals on it. And that's why he built that one. So there's a lot of different improvements that were made. But, as the years went on, I wanted to build something a little better, and the CANtact Pro became sort of the design for that. The goals for it were to make a 2-channel device, because you will often find cases where you want to have 2 separate channels with high-speed USB as opposed to full speed, so that we could do faster data throughput. And the reason for that is I wanted support for CANFD, which is the flexible data CAN. This allows you to have frames that are up to 64 bytes instead of 8. So yay, 4 times the payload. But it also allows for a higher bit rate to happen during the data phase, which essentially allows for a higher throughput overall. So instead of being capped at 1 megabit with traditional CAN, you can go up to 10 megabits in that data phase and push a lot more data through in the same amount of time. Then also the 64 bytes lets you actually start to do things like data signing, or at least doing message authentication codes, because you have enough space to actually put a counter and a MAC value in there. Single wire CAN support is also something I wanted, just because there's a lot of legacy GM vehicles, at this point mostly legacy, that use this single wire CAN, and there's not really, or at the time there wasn't an open source tool out there that had the hardware support for it. And electrical isolation, just because most of the better tools have that. The idea with isolation being that you aren't going to get a high voltage transient that ends up coming through to your USB port and blowing your computer up. I'd much rather you blow up this device than blow up your laptop. And lastly, put it in a case. I broke a lot of these things because, you'd put them in your backpack or whatever and you'd smash them up. So I wanted a decent case, and that's what I ended up putting this in. So the 2x CANFD interface and single wire CAN, a big part of that was choosing the right microcontroller. I ended up with this LPC device from NXP, an ARM Cortex M4 device that it had 2 CANFD and high-speed USB, and really it was one of the few devices out there that had all of that. It also has a ROM-based USB bootloader, which is really nice when you're developing an open source hardware product, because you want people to be able to flash it themselves without having to do JTAG and have a JTAG adapter and all that, just in case they are playing with it or they brick it. So this has a USB bootloader where you can hold down a button when it boots up and it becomes a mass storage device. You just copy a hex file over and it flashes. There's also this great development board available, which was had a CANFD shield on it, which more or less was a lot of my product. So in terms of getting the software up and running, this was a great thing to have. And then for single wire CAN, I ended up using some single throw analog switches that would allow the CAN lines to be switched between a high speed for CANFD transceiver, so the MCP 2561, which is a dual CANFD transceiver from Microchip, and this NCV 735, which is the single wire CAN transceiver. So just a simple analog switch that would allow those signals to be flip-flop back and forth depending on what mode you needed. Isolation. So again, isolation was a goal here, and sometimes you're plugging this into things like motor controllers or electric vehicles or whatever, if you get a ground fault on an electric vehicle or some other weird situation, you could end up with some transient voltage that might cause some damage. And not ideal is destroying like a $150 CAN tool, but really bad would be blowing up at least the USB port on your laptop and potentially the whole thing. So that's why a lot of these devices end up isolated. Now, isolated CAN transceivers do exist. However, at the time, there wasn't many options for CAN-FD, and there was no options that would let me do CAN-FD and single wire all in one. And so I ended up going for sort of a discrete isolation solution here. So the Scilabs Sci866X family is a very neat chip that their block diagrams there. Basically, it uses a RF modulator to send the signal across a isolation barrier, and then it gets demodulated, it goes out the other side. And interestingly, they have these chips in different variants that will allow you to have 2 channels going one direction, 2 channels going the other direction, or 4 channels in one direction. So you can sort of pick the one you need for your application. So for the CAN signals, I used these because they go up to 150 megabits per second, which is more than enough. And they provide 5 kilovolts of isolation, which is more than enough. For the simple GPIO, just the mode switching and just some of these very low speed pins, a good old optocoupler does the trick because they're very cheap. So this is a device that you run some current through an LED and it gets picked up by a receiver on the other end that it's just a photosensitive transistor that ends up creating a connection. So these work for slow signals, but they are 1,000 times slower about. So that's why you can't really use them for the high speed stuff. And then the last part of the isolation, this is for the signal isolation, but you also need isolated power. And for that, I ended up with this Recom 5-volt isolated DC-DC module. These are a very neat part because if you don't want to deal with designing and laying out your own isolated DC-DC, which I did not, it's sort of an all-in-one solution. The only problems are they're not the cheapest, but also this was sort of the highest failure rate. So I had a handful of devices that came in and failed or did not work or passed testing. And with one of them, it was because the DB9 connectors on it were, one of them actually, they somehow used a male pins, but a female shell. And I don't know how that happened, but that DB9 connector was toast. And all the other failures, which was just a handful, like maybe 1%, or less than 1%, was the DC-DC module that had failed. And those just shorted across and got real hot when you plugged them in. So unfortunately, yeah, those nice device does the trick, but seems to have a failure rate higher than I would like. So if you're designing a device, I've made the mistake many times thinking, oh, well, how hard is it going to be to put something in a plastic box? And it turns out it's much harder than you expect. So the problem with this always is that you need to think about this from the outset. It's really hard if you designed a PCB, you spun it, you have a final device, and then you want to put it in a case. And I learned this the first time around, so I realized, hey, we're going to do this from the beginning. I'm not good at CAD or mechanical engineering, so what I did is I called up a friend who is, and we settled on this company called Polycase. They do prefab cases and then they do custom cutouts. Now, if you're building, a low volume, this is going to be the way to go, just because the startup cost for it is $100 and the per unit cost is, well, not cheap, but not ridiculous. Whereas with, injection molding, custom injection molding, you have a very high startup cost, but then your per unit cost goes way, way down. That being said, the key with choosing this early was I could design a PCB that fit the case and had the right mounting holes and was the right size, and all of that had the right amount of space between the board and the cutouts. And so then I just contracted a mechanical engineering friend to do the CAD for this and put the right holes in the case. Conveniently, Polycase gives you a base model, and you can use that to just customize. So that's sort of the hardware piece, but software is kind of the critical bit to make this work. SocketCan remains the best supported and most used thing for this. It's what has the most time on it and what most people are using. And SocketCan is part of the Linux kernel. CAN devices basically just become like any other network device. And you can do, if config can 0 up, and it brings the device up. And this is actually quite, it's great because there's just lots of tools out there. So you can open a CANBus and Wireshark. There's this CANutils package that's in every major distribution now. It does basic sending and receiving. And there's a ton of other tools out there that are built off of SocketCan. This targeted the GS-USB driver again, because it's in the mainline Linux kernel. And I didn't need to, do anything to get it broadly supported on, most people's devices. Unfortunately, GS-USB does not support CANFD, so there is a modified driver. I'm working on getting that merged. I have a patch for it, working on figuring out how we can get that into the Linux kernel eventually, so that that works out of the box as well with SocketCan. But this is sort of the main piece of support, and again, the tooling out there is pretty good. Originally written by the folks at Volkswagen, actually, the SocketCan support for Linux kernel. But, that's only Linux. And I wanted to work towards some cross-platform support. And this is a bit of a work in progress still, but it is working. The key here is, for cross-platform, you're going to need a driver for every platform, right? So by default, if you're looking at writing a driver, on Linux, that's going to end up with one API to deal with writing a kernel module. Windows, you got to write yourself a Windows device driver. And then on Mac OS, I honestly don't even know how you would do that in the Mac OS kernel. But what I ended up looking at was LibUSB, and that's a user space driver for USB. That's it's been used in quite a number of things. However, I also really wanted one code base. Like I didn't want to have to write a different driver for every operating system. And Rust ended up sort of being the magic solution to this, which I'm surprised that it actually worked out the way it did. But basically with this, one Rust library ends up being able to build on Windows, Mac OS, and Linux, and then provide a USB driver on all of those systems. And there's no pound defines, there's no, special like files that are only compiled on Windows or on Linux. It's legitimately one code base, which I really did surprise me, to be perfectly honest. So LibUSB is a great library for that. The only thing is that if you are trying to write a LibUSB driver, you have an option of an asynchronous or a synchronous library. The synchronous library is very simple. It allows you to interact with the device through polling. So you ask the device to give you some data, you wait, the device comes back with the data. It's too slow for something like CAN. And because of that, I ended up switching to the async driver, which is much less well supported in Rust, at least, but that allows you to actually get much better throughput, closer to what you'd have with an actual kernel driver. And it works out quite well. So you end up with Rust support as well as being able to have C support. But Rust is a great language for writing, systems stuff, but it's not fast. It's, steep learning curve, a lot of effort to get things working. So for a lot of cases, Python is, a much better hacky language, I'll say, when you want to just script something up and make it work. And so the Python CAN option it's a library that's been out there for a while for doing CAN in Python. It's cross-platform, supports a lot of devices. And now it also supports the CANtact devices, either through SocketCan on Linux or through that cross-platform driver everywhere else. So this Python library, it opens the door for a lot of things, because using the Python CAN ISOTP, you get support for that CANTP layer that I was talking about in software. Using the UDS on CAN package, you get the ISO 14229 support. So you can write your own scan tools very quickly. It's a very easy way of doing it. And then there's a lot of other stuff that's supported through Scapy. If you haven't played with Scapy before, well, it's a great language for dealing with packet encoding and decoding. They sort of have their own DSL that makes that easy. but it also now has a ton of support for automotive specific items. And that is extremely useful if you're trying to build out either like fake being a scan tool or even fake being an ECU and talking to a scan tool. It gives you a lot of tooling that makes that way easier than doing it by hand. The way this actually works is a module or a Rust library called Pyo3 or Python trioxide is used to generate the Python module from Rust. And then whenever you build this Python module, it gets distributed out so people can install it using pip. And that's done by GitHub Actions. So whenever I tag a build there, it automatically builds the Python module using Rust, publishes it to PyPy, and then you can install that using pip. So yeah, the whole process has been automated out to make that pretty simple to push new releases when stuff breaks. Speaking of stuff that breaks, Busmaster, I'm just going to gloss over. It's an open source Windows software from Bosch that does CAN, and there is some CANtact support for it now, but Busmaster is pretty dead, it looks like. So, but this did result in a C bindings that you could use on Windows or Linux, either as a DSL or a shared object. So just a little bit about the story of building and selling the device. So I have a CM that builds the PCBs. They use the same CM as before, and using CMs nowadays for this stuff is, the price has gone way down since when I started looking at it. It's very reasonable to have your stuff built by some CMs. The cases are manufactured by Polycase, as I said. They customize them and make it so all the cutouts are there when they arrive. And then I have been doing final assembly of these, which is, you put on a movie and get some screws and electric screwdriver out, knock them together. I ended up launching this through Crowd Supply, which is a service that does sort of the Kickstarter for open source hardware. I highly recommend them if you're interested in launching an open source hardware project. They really help you get through the process, and then they end up also partnering with Mouser to get really good fulfillment channels. So if you're interested in that, I would advise going through them if you'd like. And just some final notes here. So if you're looking to build some open source hardware, just some things to think about. BOM cost is critical because everyone wants to cut. So if it costs $10 for the bill of materials, you're probably going to need to MSRP the thing for at least double what your costs are, and then you still have to get it assembled. So $10 in BOM costs, maybe by the time it all gets put together, you're looking at $20, and then you're probably going to end up having to wholesale that for double, and then you want to make some profit off it as well. So these start to stack up with hardware pretty quickly. With open source hardware, I think you really do need to be building it for yourself. Open source hardware, right today at least, isn't a great business. You build stuff that you think is cool, and other people might think it's cool as well. I think you can leverage open source hardware to build out other tooling and build out other business, but it's a hard business in of itself to sell hardware. Don't build in a vacuum. So show other people your products, get feedback. There's a lot of people that I sent pre-release boards out to that played around with it and found problems and recommendations. So I recommend doing that. And then the other thing is always finding vulnerability, or not vulnerabilities, but just bugs, errors in your stuff. Just because it works on your computer doesn't mean it works on everyone's. So that's another good reason. And chip shortages suck. We're currently sitting in hopefully getting towards the tail end of a pretty big silicon shortage, but who knows? And that's a real pain, unfortunately, to deal with. I currently am not, I'm waiting to get some more boards produced for inventory, and yeah, the microcontrollers aren't necessarily available right now. So that is the thing that you do end up dealing with. We're pretty short on time here, just coming to the end. A few demos I can normally do, but I'll just say the next steps for this. The Rust command line interface, it needs some love. Again, the Linux support for SocketCan is really the main thing right now. So I'd like to get that more functional, at least to the level of the CANutils tool on Linux. Getting the FD support merged into the Linux kernel would be really nice. And I also want to build some breakout board for it, just so you can do OBD2 and different types of connectors easily. But yeah, just some of the ideas of next steps. So I think that brings me quickly to the end of the block here. Again, thanks for sticking around, and hope that was of some interest. If you want to play around with CAN, this is one option. And it's fun to see build a hardware tool and see people fork it and do stuff with it. And I get people asking like, hey, can I take this and work it into some other design? And so that's always interesting to see and see what people have done with it. So it's great to take stuff and put it out there and see what happens. Yeah, thanks again, and thanks to the hardwear.io folks for having me around. It's always a good event, and hopefully see you folks in person in the near future at the next one.
All right, thank you, Eric.